Good morning and welcome to the October Pacific Northwest DEWS Drought and Climate Outlook webinar. Thank you to those who have joined us previously and those joining us for the first time today. My name is Britt Parker and I am the National Integrated Drought Information. I'm with the National Integrated Drought Information System at NOAA, and I am the coordinator for the Pacific Northwest DEWS. This bi-monthly webinar series is hosted by NITUS, CERC, and the Northwest Climate Hub. It's designed to provide stakeholders and other interested parties in the Pacific Northwest with timely drought and climate information. Each webinar will be tailored to reflect recent, current, and forecasted conditions and climatic events, but will also include discussions of observed impacts and other related updates from across the region. Webinars and recordings and other supporting materials will be posted on drought.gov later this week, and you'll receive an email when those are up on the website. Please note that after today's webinar, you will have the opportunity to provide feedback that will help us improve this webinar series, so please take a moment and tell us what you think. On our agenda today, I will provide the overview and the introduction to NITUS and the Pacific Northwest DEWS. We'll have a climate recap and current conditions from Kelsey Jensko from the University of Montana and the Montana Climate Office. Then we will hear about the seasonal conditions and climate outlook from Mike Halpert with the National Weather Service Climate Prediction Center. After that, we'll have two presentations, one from Oriana Chedvigen with the University of Washington on how models affect hydrologic climate impact studies in the Pacific Northwest. And then a slight change, we'll have evaluating gridded drought indices to enhance the Upper Missouri Drought Early Warning System from Zach Hoylman, a colleague of Kelsey's. So we're going to hear from that presentation from Zach instead of Kelsey this morning. We will be using the Q&A box at the right side of your screen for questions during the presentation, and we'll address those and additional questions during the Q&A period after the four presentations are complete. So I first want to introduce our partner host. The Pacific Northwest Climate Impacts Research Consortium, or CERC, is a climate science to climate action team funded by NOAA's Regional Integrated Sciences and Assessment Program. CERC supports communities, policymakers, and resource managers in Oregon, Washington, Idaho, and Western Montana as they work to adapt to the changing climate. Our next partner is the Northwest Climate Hub, which develops and delivers science-based, region-specific technologies and practical information that will assist agricultural and natural resource managers with climate-informed decision-making. And then I'll talk a little bit about NITUS and the Pacific Northwest DEWS before we jump into our presenters. So NITUS's mission is to improve the nation's capacity to proactively manage drought-related risks by providing those affected with the best available information and resources to assess the potential for drought and to better prepare for, mitigate, and respond to the effects of drought. We want to improve our understanding of how and why droughts affect society, the economy, and the environment to improve accessibility, dissemination, and use of early warning information for drought risk management. Our approach to achieve that goal is to build the foundation of a national drought early warning system through the development of regional DEWS, where networks of partners and stakeholders share information and actions that can help communities cope with drought. While the ultimate goal is a national early warning system, we recognize that impacts and early warning information differ across the region. Each DEWS has many of the same base ingredients, but ultimately have their own flavor to reflect the needs of their region. The Pacific Northwest DEWS was officially launched in February of 2016, and our strategic plan is available on drought.gov. But please note we are in the process of updating the strategy now, and there'll be a little more information in a moment on how you can be involved. So please mark your calendars for our next webinar on December 16th of 2019, our final webinar this year. Registration information for these and other webinars can be found on drought.gov. Also note we have two water year recap and outlook meetings coming up in November, one for Oregon, Washington, and Portland on November 5th, and one for Idaho in Boise on November 18th. And those The registration information will also be put up on drought.gov this week, and you'll find that in your post-webinar email you'll receive later this week. And finally, I mentioned that we are updating the Pacific Northwest DEWS Regional Implementation Plan for the period of 2020 to 2022. I'll be giving updates on the content and process at both Water Year meetings, as well as on the November Pacific Northwest Tribal Climate Change Network conference call. So please attend, listen in, and look for more information on the Pacific Northwest DEWS emails on how you can contribute, or email me at any time. To facilitate our early warning system, more precipitation observations are needed, so we encourage you to join COCOROS, the Community Collaboration Rain, Hail, and Snow Network. This is a unique, nonprofit, community-based network of volunteers of all ages and backgrounds working together to measure and map precipitation, rain, hail, and snow, as well as condition reporting. Observation by COCOROS observers of precipitation events and the lack of precipitation are important to capture and improve our understanding of weather. And I will place your COCOROS coordinators in the chat box in case you want to become a member and get involved. And so with that, I will turn the presentation over to Kelsey to talk about our climate recap and current conditions.
Okay, hey Britt, are you getting my notes screen, or?
I am seeing your notes screen right now.
Let's switch this. Sorry, everyone. Okay, that should be good. Thanks, Britt, and hello to everyone. I'm excited to be here to present the Climate and Drought Outlook today. You know, I think we all know that we've had some wet and cool weather in the last month across the Pacific Northwest. Looking out my window right now, it's a winter wonderland. We had about an inch of snow on the ground here in Missoula this morning, and it's still continuing. So it's time to put on some rock skis and head to the mountains. So my agenda today, or for my portion of the presentation today, I'm going to focus on how the conditions we've experienced in the last couple of months compared to historical conditions, or the historical record. Specifically today, I'll focus on our 3-month temperature and precipitation rankings, so July extending through September. I'll talk in a little bit more detail about some of the records and rankings that we experienced in September, and then I'll kind of follow up with our precipitation and temperatures thus far in October. We're near the end of the month. I'll talk some about soil moisture conditions across the larger region, streamflow, our snowpack conditions, and ultimately what that means in terms of drought. It shouldn't be a surprise to folks that we're at a point where there's not significant drought across the region, actually no drought, slightly abnormally dry conditions in the panhandle of Idaho. So jumping right in, let's start by taking a look at temperature and precipitation rankings for the last 3 months. These rankings that I've shown here are from NOAA's National Center for Environmental Information. And here we're comparing July through September temperatures and precipitation to conditions that have occurred over the course of the last 125 years. So as an example, larger numbers up to 125 or the 125th year would indicate very warm conditions. That would be indicated in red, or very wet conditions, which would be indicated by blue to dark blue shading. Smaller numbers down to 1 indicate increasingly cooler temperatures, and that would be indicated by light blue to dark blue, or very dry conditions in brown. The figure that I've shown on the left shows temperature ranks by climate division, so at a smaller scale than the state itself or the statewide average, so by climate division across the states. What I'll point out is that the area that really stands out here is western Montana, and almost the entirety of Idaho, so northern to central Idaho. Here, temperatures have been above average for over the course of the last 3 months, and this is consistent with drought conditions that we're seeing in these regions during the summertime. Portions of western Washington and Oregon along the coast have also seen above average to much above average temperatures. For the remainder of the region, we've seen near average temperatures for the 3-month period, but as I'll show in upcoming slides, it has gotten much cooler in the last month especially. Moving to the figure on the right, the 3-month precipitation rankings are above average to much above average for the majority of the region, except for central to northern Idaho and portions of eastern Oregon. Okay, so let's move forward into what we've experienced in the month of September, and there were a lot of records set in September. The figure on the left shows temperature ranks by climate division across the states. The area that really stands out here in terms of above average temperatures is, again, western Montana, but the majority of the region saw average temperatures for the month of September, except for small portions of central and eastern Oregon with slightly below average temperatures. All right, moving to the figure on the right, the September precipitation rankings are above average to much above average for the entirety of the region. For the states as a whole, if we look at the average conditions across the state, Montana saw its second wettest September on record, while Washington and Oregon were close behind with their 8th and 7th wettest years in the last 125 years. A lot of the moisture, I'll highlight that a lot of the moisture for September came with a historic snowstorm in September's final days. So around the 29th of September, storm blasted parts of the northern Rockies and Cascades with heavy wet snow and especially high winds. More than a foot of snow fell in parts of northeastern Washington. Spokane got much less, but it was the city's first recorded September snow since 1926. In Oregon, the National Weather Service reported wind damage from gusts up to 55 miles per hour in Portland, and hail was also reported. Cascade Mountains got up to 10 inches of snow from the same event. And really the highlight of this event, the top snow totals from the storm was around 52 inches in Babb, Montana, about 10 miles south of the Canadian border, and 5 additional locations in northwest Montana tallied up more than 40 inches of snow. So as a whole, we're off to a pretty good start for our winter snowpack because of that storm. Okay, so let's move forward into what we've experienced for the month of October. I'm going to show 2 images of temperature and precipitation from the Climate Impacts Research Consortium and RISA's Climate Mapper Toolbox. In this slide, I've shown temperature departure from the mean, and this extends from the beginning of October until the 26th, so about 2 days ago. Temperatures from this window of time are compared across the period from 1981 to 2010. If white values occurred, or if there was white shading, that would indicate near normal temperatures. White to blue shading represents colder than normal temperatures, and red shading would indicate warmer than normal temperatures. It's kind of silly to talk about temperature scaling with this image. There's not really a need to describe that. The entire map is blue, indicating temperatures that have been consistently 3 to 4 degrees Fahrenheit below normal. One of the results of these cooler than normal temperatures is that along the Rocky Mountains and Cascades, precipitation that has fallen is accumulating as snowpack in our middle and higher elevation basins. So we're starting to see the rapid development of our winter snowpack even as early as the beginning of October. Okay. Here's a look at precipitation since October 1st, and again, this is as a percentage of the mean value from 1981 to 2010. As an example of how to read this image, dark brown areas would represent 0 to 10% of the mean, or little to no precipitation. White to light green areas would represent approximately 100% of the normal precipitation for the time period. Dark green shading indicates upwards of 200%, or almost 2 times the normal precipitation. For the northern portions of our region, we see a lot of green indicating above normal precipitation. Portions of eastern Washington, extending into the panhandle of Idaho, have seen in excess of double their normal October precipitation, as indicated by dark green shading. There is a zone of dryness that extends from the leeward side of the Cascades in Washington down through and into Oregon. Additionally, southern portions of Oregon and Idaho have had little precipitation over the last couple of weeks. Here, values range from 10 to half of the normal precipitation that we would typically receive in October. Okay, So let's talk a little bit about where we stand in terms of average snowpack conditions for the beginning of winter. Snowpack is used as a key indicator that can foreshadow drought conditions moving into the spring and summer. I'll highlight that it's still way too early to tell, but we're off to a good start this water year. I've shown the percent of average snow water equivalent for October 26 across the mountain regions of the Pacific Northwest. These data are measured from snow water equivalent at NRCS snow pillow sites across the Rocky Mountains and the Cascades. And just as a way to think of snow water equivalent, it's the amount of water that would exist as a depth of water if we were to melt a vertical column of snowpack for a given area. In this figure, I've shown snowpack, snow water equivalent conditions for the Huck 8 watersheds across the regions. Red to orange shading indicates below normal snowpack conditions. White to light green shading would indicate a normal snowpack. And blue represents much above average snowpack, upwards of 200% of normal. So generally what you see when you blur your eyes across the region, basins in western Montana and Idaho, west of the Rocky Mountain Divide, are all about 200% or greater of their average annual snowpack for this time of the year. This is really good, but I point out that percentages can be a bit deceiving this early in the year. Large early season storms, like the one we received in late September, can cause these numbers to seem really significant. As an example, if the normal for this time of year was 2 inches of snow water equivalent, and we have 4 inches on the ground, then we would be at 400% of normal. So time will tell if these conditions persist and we have a record-breaking snowpack. Moving further west, the Olympics in northwestern Washington are currently less than 25% of their normal snow water equivalent. In the Cascades, extending downward from northern Washington to central Oregon, conditions are generally normal to much above normal. Here, the snow water equivalent ranges from 100% to greater than 200% of normal. So generally, and taken as a whole, these conditions suggest a pretty good start to our winter snowpack. Okay, so the increased precipitation that we saw in the late summer and into the fall kind of alleviated drought conditions that had occurred across the region in some areas in the summertime, and it's begun to set the stage for soil moisture conditions across the region. Soil moisture is factored in the forecast as an indicator of wet or dry basin conditions or initial conditions, and the potential for drought can give an indication for the potential for drought as we move into the spring. I've shown here the Climate Prediction Center's modeled soil moisture percentile ranking for October 26th. Percentiles from 1 to 30 would indicate soil moisture deficits in dark red to yellow shading. Normal soil moisture conditions are indicated by percentiles ranging from 30 to 70, and these are indicated by white shading, and surpluses of soil moisture are indicated by light green to dark green shading. So what you see for our region, the majority of the region has near normal soil moisture percentiles as indicated by white shading. Areas that stand out in terms of above normal soil moisture percentiles or surpluses include the southern portions of Oregon and the Idaho border and the northwestern portion of Washington, especially around the Puget Sound region, which received significant amount of rainfalls last week. Okay. Looking directly at current stream flow conditions, here's a map of USGS stream gauges and the average flow rankings across the Pacific Northwest for the last week. Okay, so this is an average across a 7-day time period. Across the gauge network, blue symbols indicate greater than 90th percentile flows for this time period. Light blue is between the 76th to 90th percentile. Green is 25th to 75th percentile or about normal conditions. And orange is the 10th to 24th percentile or below normal stream flows. One thing to note is that many gauges aren't currently appearing on the map. In some cases, this can be due to frozen stilling wells, but also just river conditions at the gauge site. The majority of the region is showing average to slightly above average flows across the major river systems, as depicted in green to light blue symbols. The big story here is the western portion of Washington and the Puget Sound area. Steady rainfall and significant rainfall from the last week contributed to much above normal flows surrounding the Puget Sound region. There are still some localized areas of below normal flows. These include portions of the northwestern Montana along the Flathead River, the Snake River in southern Idaho, and upper reaches of the Willamette River in Western Oregon. These are areas of below normal flow, and they're associated with long-term impacts of the summer drought that was present in some of these regions this summer. Okay, so summing all of these observations up, let's take a look at last week's drought monitor. This was drawn up by Richard Heim of NOAA's National Center for Environmental Information. And generally, what you see is on the weeks map, there's still a sliver of abnormally dry conditions in the northern panhandle of Idaho. It'll be interesting to see if that changes given all of the recent snowfall. But with above normal precipitation and near normal temperatures in September, there were significant and large improvements made to Washington's drought conditions over the last several weeks. The abnormally dry or D0 areas that had been present in western Washington and Oregon received 2 to locally over 5 inches of precipitation last week. And this was enough to end abnormally dry conditions, or that yellow shading in those areas. So, what I'd point out is currently there's no drought in the region, and only 1.4% of the area is abnormally dry. We haven't seen this little drought in our area since May of 2017, before the flash drought that occurred in the High Plains. So we're doing pretty well going into the winter time period. So to conclude the climate and drought summary, what I'd highlight generally, temperature, it's been 3 to 4 degrees cooler than normal across the region over the course of the last month. For precipitation, it's been wetter than normal in the northern portions of the region, so Montana and Washington, and slightly drier in Idaho, and slightly drier than normal in southern Idaho and Oregon. Our snowpack is off to a good start. The Cascades and Rockies are accumulating snowpack with cooler temperatures and a few large storm events that have occurred. And these conditions are contributing to recharge of soil moisture and increased soil moisture in some locations. We're typically seeing much above normal stream flow in localized areas, especially in the Puget Sound region, and generally no drought across the region as a whole. And I'll stop there.
Great. Thank you, Kelsey. I'm going to turn it over to Mike to talk about the seasonal conditions and climate outlook.
Okay, thanks, Britt. Hopefully my screen should be up if all our testing paid off.
Yep, looks good.
Okay. This is amongst, I've been doing this a long time. Generally, some forecasts, at least we have more to base our seasonal outlooks on than we have certainly for this year. I will still go through a kind of a canned set of slides, always starting with the El Nino Southern Oscillation. We have an alert system that has basically watches and advisories, and it can also be, as it says right now at the top of the screen in red, NA for not active, which basically means that we do not have El Nino, so we have what we call neutral conditions. And as the fourth bullet says, we think that will continue through the fall, really the winter, and even into the spring with a fairly high confident rate of 55 to 60% chance of that. So, I'll go through and explain where that comes from. Here we're looking at our main index for El Nino. It's a very simple index. It basically looks at the ocean in the middle of the east central equatorial Pacific Ocean. This is a table that shows, I guess, the last 12 or 13 years, these seasonal values, what we call our ONI, the Oceanic Nino Index. You can see that the red numbers at the bottom of the screen, starting with September, October, November of 2018, going through MJJ, which stands for May, June, July of 2019, those are all colored in red, that at least in a historical sense, show that we had El Nino, in particular during last winter and spring. The reality is this is overly simplified, and while this is a nice number and an easy way for folks to characterize things, El Nino requires more than just the ocean warming. It requires some changes in the atmosphere above the ocean. And for folks paying attention, and I think I did one of these calls last February, it was really not until early February that we had felt that there was enough of a change in the atmosphere to change our El Nino watch into an El Nino advisory. You can see the last couple of points here down at the bottom, June, July, August, that's JJA, and July, August, September are very near zero, actually 0.1 for the last season. So firmly in the ENSO neutral category. This is looking at the last 4 weeks. It's actually not quite the last 4 weeks because I didn't get a chance to update it this morning, but it's a fairly recent snapshot of departures in the tropical Pacific Ocean, sea surface temperature departures. The blue box is that Nino 3.4 area, the area that forms the basis for our oceanic Nino index. And at this point, they are most of the anomalies or departures in that box are above normal. They're not all that large above normal. I think for this would probably be very close to our threshold of 0.5. Interestingly, that to the west of this, so to the, from about the international date line westward, we see much warmer or larger departures. And really the eastern part of the basin right now is on the colder side. So it's a fairly interesting layout of temperatures, but really not particularly significant in terms of disrupting the atmosphere above it. Here's looking at a plot that we call a Hofmuller, or a time longitude cross-section of those same sea surface temperature departures. So starting up at the top is a year ago, so that's late October. Really, if you look at the whole plot, you can see varying shades for the most part of yellows and oranges. So that's all highlighting last late winter and spring's El Nino. As we got through the spring into the summer, in particular towards the middle and late part of summer, and you start to see some blues show up, and that's when the ocean actually became a little colder than normal. And again, though, beginning in maybe mid-September towards the bottom of the plot, you can see that the yellows are again encroaching more towards the right side of the plot, which is the eastern part of the basin. So when you get to the very bottom of the plot, you can see that a lot of the ocean is on the warmer side, but they are the lighter shades of yellow. So while warm, not quite at the El Nino threshold. These are time series of various regions across the Pacific. You can see that on the left slide of the plot. There's different boxes. Nino 3.4 is the one in the middle, and that's what those that's the key area for seeing kind of teleconnections, as we say them, or links outside of the tropics that could influence temperature and climate across North America. So if you look in the time series of the sea surface temperature anomalies, the second figure down says Nino 3.4. So again, that's the key area. You can see again, there's a lot of oranges there, not hugely orange. If folks remember back in 2015-16, those departures were certainly well north of 2 degrees for a good deal of the time. Here they generally hovered maybe around 1, sometimes much less than that. We did see the end of the event in the summer. It went slightly cold, and really over the last couple of weeks, we've been on the warmer side. I did get a peek at the value for this week, and it has dropped a little bit from 0.8 to 0.6, and we actually would expect that to continue as we go forward over the next couple of weeks. This is now looking at what we call the integrated heat content, and this looks below the surface. And the reason why we look below the surface across the Equatorial Pacific is a lot of times that gives us clues as to what's going to happen at the surface. Main takeaway from this is that while we do see above average temperatures below the surface, and that's on the far right of the plot where it says October, you can see if you compare it to the far left of the plot, those values are maybe half of what we saw last year at this time. So again, while on the warmer side, not all that warm, and if you think back to last winter, even with departures below the surface twice what we are now, we still only barely managed to eke out El Nino. So while the ocean is warm, We're certainly not seeing the characteristic patterns of rainfall across the Pacific Ocean. That's what this plot is trying to get at. We call it outgoing long-wave radiation, or OLR anomalies. It's basically an indication of where it's either raining more or less than normal. All of the red areas to the west, so all the way from the Indian Ocean across Indonesia out to the dateline, all those oranges are areas where they're actually seeing less rainfall than normal. Certainly not an El Nino pattern. In an El Nino pattern, you would expect to see it be wetter than average, centered around the dateline. The dry areas over Indonesia and to the west would be consistent with that, but there's, again, no dipole. It's just a very, very, maybe a little bit unusual, but it's literally just dry, really from the dateline all the way across into the eastern part of the Indian Ocean. Going forward, do we see El Nino developing? These are a bunch of different models, and sometimes I think we have too many models, but we certainly have a number of models to pick from. These are either runs from mid to late September or early October on the right. I have circles drawn over the winter seasons or the winter months. And then you can see solid red lines that extend across at +0.5 and -0.5. Again, kind of the thresholds for El Nino. So one of the takeaways is that we really have very few lines, if any, that go below the -0.5 line. So we really have no tools that are forecasting La Nina this year, and that's really not too surprising given that the subsurface is on the warmer side. And again, that's usually a process and usually an indicator of what we expect to see. There are a number of models that are on the warmer side, in particular in the plot on the left that says IRI/CPC. So there are some models that are forecasting what would be another winter of a weak El Nino. On the right is what we call our North American multi-model ensemble. Again, for the most part, and the dashed line in the middle is the mean of all those, really are hugging very close to the neutral range. So it does give us a fair degree of confidence that we'll see neutral conditions. On my last predictive slide here, this is our own model that we run at the Weather Service called the Climate Forecast System, or CFS version 2. Again, probably the relevant slide is the time series to the left that shows, while a fair degree of spread of various model runs, the means are again in the 0 to +0.5 range. So maybe the warm side of neutral, but still neutral all the same. So the forecast team, and this is from early October, is with a fair degree of confidence favoring ENSO neutral conditions, again, really into the spring and beyond. The next best choice here would be El Nino, but still, maybe in the 25 to 30% chance with a fairly low likelihood of La Nina developing anytime soon. The forecast, before I present it, does leverage or does acknowledge ENSO neutral, so really no help in terms of for factoring something that might give us a decent clue as to what to expect this winter. For some folks, the Arctic Oscillation can play a role, and there's certainly interest in that, but it has been positive really for the last 6 years, which is, for folks that follow this closely, that would be surprising to some. When all else fails, we have models and we have trends. Trends in general for temperature are fairly small, but on the warmer side over good chunks of the country, not so much actually right now in the Pacific Northwest. They're fairly flat. Last winter's normal to cold is factored into that. And again, the forecasts that I'm about to show were issued in October. We will take one last look at winter. I think it's November the 21st this year. So here is the outlook, and I want to first highlight the fact that this is a probabilistic forecast. So this is not a guarantee by any means. I'll also highlight that the probabilities If we look at you'll see various shades of orange and no shades of blue, which implies we don't favor below average temperatures anywhere. It doesn't mean it can't happen. And if you look at some of my examples, like in Eastern Oregon, while the probability is in the low 40% chance of above, it's still 1 in 4 that you'll see a colder than average winter there. Some areas further in the middle of the country are, I guess you'd say, the areas most likely to be coldest winter, but that's still the normal or the base probabilities of 1/3, 1/3, 1/3. So no part of the country has a likelihood of greater than 1/3 of being colder than average. Some areas, particularly up in Alaska, have a better than a 50% shot of being above average. We go to precipitation. Here it's tilting on the wetter side across much of the north, not so much in the Pacific Northwest, although I guess it does extend into western Montana. There is a slight tilt towards dry in central and northern California, maybe just touching southern Oregon. Again, the largest probabilities are again up in Alaska, where we exceed 50% chance on the wetter side. And finally, the drought outlook. And remember, this only goes through January. The other plots we were looking at were actually for December, January, and February. No drought in the Pacific Northwest, and at least at this point, we don't see any developing. Looking at the rest of the country, and we've actually seen a fair amount of improvement already since this was released in the southeast. Persistence in much of the southwest, and probably maybe the noteworthy part is the potential for development in California. And I probably used up my 10 to 12 minutes, so let me pass it back to you, Britt.
Great, thank you. And I'm going to go straight into Oriana's presentation. So I'm giving you control. And just to answer a quick question as we do that, slides will not be posted on the website, but I'll have email addresses on the last slide before we wrap up, and you can email me or the speaker if you'd like slides. So Oriana, take it away.
Great, thanks, Britt. And yeah, I really do encourage people to email me if you have any questions. I really like answering questions about my work. So I'll be talking about some work that I've been doing in the Pacific Northwest, looking at how our modeling choices, so how our experimental designs impact the final answer about how hydrology will change in the future due to climate change. In case you have to run, just the punchline of this talk is that for dry conditions, I'm specifically thinking about drought conditions or people working in arid areas, your choice of hydrologic model can have a really big impact on your climate change predictions. Also, you can find all the figures from this talk in a paper I published in Earth's Future in 2019. So if you're looking for any of this eye candy, you can find it there. And also all of this data that I'm showing is publicly available at the website shown here. And if you can't jot it down, just email me and I can send you a link to that. But all of it's available there and people are using it to conduct their own climate impact studies in their basin of choice in the Pacific Northwest. So here, I'm working in the Pacific Northwest. I'm largely modeling the Columbia River. So shown here at Vantage, Washington, and the black line across the river there, that's the I-90 bridge, if you've ever crossed the Columbia at Vantage. And about 5 miles downstream of that is the Wanapum Dam. And so the Columbia River is highly managed for a variety of reasons in the Pacific Northwest, ranging from flood risk management, the hydropower, irrigation, ecosystem services, navigation. And there's water managers ranging from very large federal agencies down to small utilities, irrigators. And many people in their long-term planning are trying to figure out how climate change will impact their water resources. And so to that end, they conduct hydrologic impact studies. And these studies are a way to link climate projections of the future up to maybe 100 years from now to on-the-ground impacts to small streams or large rivers. And all of them follow this general pattern of linking models. So they take different emission scenarios or ways of mimicking, of representing the way that we'll emit carbon into the atmosphere. They link it to Earth system models, like kind of similar to the ones that were referenced earlier in the El Nino talk. And then they use downscaling and bias correction techniques and different hydrologic models, and they link all these different models, this alphabet soup of models, together to create projections of stream flow. And the question that I have is, to what extent do each of our choices along the chain impact our final result? So whether you choose model A or model B, how much does that actually impact your river and your specific question? So whether it's about drought or floods or something like that. So what we did was we designed an experiment in which we ran lots of different combinations of all these different options and combined them. So I'm just going to go quickly through each of the different steps so to make sure we're all on the same page. And so representative concentration pathways are these emission scenarios, and it's ways of representing future release of greenhouse gases into our atmosphere. And for our case, we use two different of these RCPs. The red line shown on this graph shown here, and that's kind of a burn it all scenario you could think of, in which we burn all of our fossil fuels. And then we also used a mitigation scenario, which is shown in the light blue line here in the emissions going out to 2100. And those are in which we actually enact mitigation measures. We then took those emissions and we put them into 10 different global climate models, which are just representations of the Earth system that incorporate these elevated greenhouse gas emissions, and then see how our Earth system, so our atmosphere, our clouds, our oceans would respond to that, largely translating into elevated temperatures and then changes in precipitation as well. Then the outputs of that, though, the goal of a global climate model is really to represent the Earth system as a whole. So how it's going to impact us in the Pacific Northwest is a little harder to understand without using something called a downscaling method. So it's something that takes this information about the world and the global climate and gives it some local flavor, you could think. It puts snow in the Cascades, for instance, where the Cascades don't actually show up in global climate models. So downscaling methods are a way to take this coarse scale information, like the map shown on the left there, down to the scale that's actually relevant for a water manager or someone who cares about snow in the Northwest. So to the scale of the map on the right. And then we ran that information out of the downscaling methods through 4 different hydrologic models. And so these are the models that actually take your precipitation and your temperatures, and it translates it into soil moisture and snow and runoff and ultimately stream flow. And we used 4 different ones of those. So combining all of these different multiple combinations of models together, we created a 160-member ensemble. And this is the data set that I'm saying is publicly available. All of these 160 traces of the future are available for people who are concerned about their specific water system and want to know how it might change in the future. So as an example of what that looks like, I'm showing here the stream flow for the Columbia River at the Dalles, which is the upstream area of which is highlighted in red in the map there. And so across for the 30 years at the end of the 20th century, so the 30 years from 1980 to 2010, sorry, 1970 to 2000, is shown as the gray traces on this plot. And moving into by the end of the 21st century, that stream flow is going to look very different. What used to be a snowmelt peak coming off between May and July is going to start to shift earlier according to this ensemble. And yet, what I'm showing here is that depending on whether you highlight that full ensemble according to this warmer RCP 8.5 burn it all kind of high emission scenario, or a more mitigation climate scenario, you see a lot of difference in your traces. So it shifts much earlier if you have if we as society emit more carbon into the atmosphere, because there will be a stronger temperature shift. Whereas it stays more like the historical period if we actually impose mitigation measures. In contrast, if we look at that same ensemble of scenarios, but then highlighted according to your hydrologic model, we also see differences. So these are 4 different hydrologic models available in this ensemble. Those highlighted in purple, the PRMS implementation, which is one hydrologic model that comes out of the USGS, they're showing a much stronger response to changes in climate than, for instance, one of these VIC implementations, a different hydrologic model that comes out of my group in Princeton at the University of Washington. It shows a much weaker response to these changes in climate. So your choice of hydrologic model actually can have a big impact on what your final climate signal is. As a way to probe that quantitatively, we wanted to know, like, how much can you actually measure the impact of these changes? So we chose an example of a metric of timing, so the centroid of timing, which can be defined here. I'm showing just a cartoon of calculating the centroid of timing. So if you look at your hydrograph through the year, the centroid of timing is the measure of when half your flow has passed a gauge, shown by the dashed line in this cartoon. And if you go into the future, you can calculate the same half the gauge when flows past the gauge, and then you can calculate a shift. And so in this cartoon, you would have a shift of a certain number of days earlier in the future. And if we were to do that for every one of our ensemble members, we would then be able to have a distribution of like a shift in this timing. And then we can do a simple statistical analysis called an analysis of variance to see how much each of our different choices impacts our spread. And the results of that I'm showing here. So shown here is the dominant decider of the spread in our projections of timing at about 400 locations in the Pacific Northwest. And what we're seeing is that your choice of RCP, or your emission scenario, is the main decider of the shift in timing of that stream flow. So in other words, if you're doing a study and you care about the timing of flow, for instance, you care about when will the snow melt, when will the rivers swell, or will the rivers swell earlier or later in the season, the choice of RCP can have a really big impact on that answer. So also, if you care about really understanding the uncertainty around that answer, it would be pretty important to include multiple different emission scenarios in your study. If instead you worry about just overall stream flow, so total overall annual volume, your choice of your global climate model is the biggest decider of that spread. So if you care about, for instance, a hydropower operator might care about just the total amount of water flowing through a river, the choice of GCM is going to have a really big impact on that. As a result, you might want to include multiple GCMs in your analysis in order to understand the spread around that answer. And then in this one, particularly relevant to this webinar, folks who care about low flows in a river and changes in low flows, your hydrologic model has a really big impact on that. That's the dominant decider for many locations on the changes in low flows moving into the future. These analyses, in my mind, are largely motivated by people who have limited resources. I tell them, we have this really big ensemble of streamflow projections, like it's totally publicly available, and they say, okay, well, we can't run 160 different scenarios. Well, given this analysis, you can make a more informed decision about selecting which scenarios you use for that analysis based upon tailoring it to what your question is. So if you care about low flows and dry conditions, it would be really important to use multiple different hydrologic models in your scenario of the scenarios that you look at. So all told, just final overall idea is that modeling choices really matter. For if you care about timing and annual volume, your climate modeling, so your emission scenario matters, and your GCM. But if what you care about is dry conditions, your hydrologic model choice really matters a lot. And with that, I'll pass it back to Bert, and I'd be happy to take any questions afterward as well. And also, don't take this embroidery to be scientifically accurate. It was my
Great, thank you so much. I'm going to hand it back over to Kelsey and Zach, and I know we're running a few minutes late today, but we will continue and let Zach finish his presentation. If you have to drop off and want to listen to that, you can always listen to the recording, which will come out, but hopefully everyone can stay with us. So Zach, we will turn it over to you.
Great, thanks, Britt. And I'm super excited to be here today to talk a little bit about evaluating gridded drought indices to enhance our monitoring system in the upper Missouri River Basin. And before I start, I just want to say that this is a very collaborative project, and there's many more people that have helped with this ongoing project than are listed here. And yeah, it's a big collaboration. So to start, I just want to highlight that drought is unfortunately a very common and pervasive aspect of our landscape in Montana, and it has many impacts on the economy of Montana, you know, from sectors such as things like agriculture and recreation to our landscape management. And in 2017, we had a relatively extreme event that we have deemed the 2017 flash drought. And this drought has spawned a bit of research looking at why this was such an extreme event. And what we see is that in 2017, the drought began, like most do, with a deficit in precipitation, but this precipitation deficit was exacerbated by really warm atmospheric conditions, dry atmospheric conditions, and windy conditions. The kind of ensemble of these different effects have created a really rapidly onsetting drought that caused drought declarations across a large portion of the upper Missouri River Basin. And this drought, as unfortunate as it was, has allowed us to really pursue a really cool collaborative grant to rethink the way that we monitor drought in the upper Missouri River Basin. And that's really what I'm going to be talking about today. This collaborative grant has two main components, and it's funded primarily by the National Integrated Drought Information Systems, or NIDIS. And the two components are, first, a upper Missouri River Basin dashboard, which is a drought indicators dashboard that is meant to be a technology transfer system to display current drought information systems to this region. And the second, which I'll really be focusing on, is this validation of drought metrics and their calculation against important indicators. And in this talk, we're going to be looking at soil moisture. So the idea here is to really understand how best to calculate different drought metrics to represent things that we're interested in, like soil moisture. But before we go any further, just really quickly, I want to think about how we monitor drought. And in general, we like to monitor drought using gridded drought indexes, or in collaboration with traditional indicators, things like Streamflow or soil moisture, and to really, tailor a specific monitoring system for the upper Missouri River Basin, we developed the Drought Indicators Dashboard, which is developed very closely with the Governor's Drought and Water Supply Committee in the capital of Montana and Helena. And that's a lot of the partners that you see at the bottom of this page are a part of that committee. And we really strive to have two kind of main things we wanted to complete with this dashboard. We wanted it to be a transparent system with transparent data usage and algorithms. So one big highlight here is that everything you're going to be seeing today is all the code that was used to develop all of the results, and mapping systems are available freely and publicly on GitHub. And they're reproducible for any region. So you can go ahead and just change some files within the code base and reproduce these data sets and analyses for any region across the continental US. So this is just a screenshot of our Drought Indicators Dashboard. The URL to visit this website is up on the top right there. And really what I just want to show you here is this is a mapping system that shows relatively wet or dry time or conditions across the region. And this metric here is the standardized precipitation index that we've calculated over a 30-day time scale. So you can calculate drought metrics over different timescales to integrate drought information over, say, a relatively short period, like 30-day, all the way up to multiple years. And I really want to highlight this because you can get very different representations of how wet or dry a region is depending on how much information you integrate into your drought information metric, right? So this is a 30-day time scale, but if we look, for example, at a 365-day time scale, you see that the relative representation of wet and dry conditions change quite a bit. And I should point out, of course, in these maps, the blues are wetter than average conditions and these reds are drier than average. So you can see at short time scales, things are very wet. But when you look at kind of these longer time scales, especially in the northwestern portion of the state and into the panhandle, we tend to see these drier conditions. And the real question here is, what time scale or what amount of information do we need to integrate to really represent these important conditions on the ground, things like soil moisture? And that's really what I'm going to be focusing on today. So how do we best apply these tools that we use across the continental US and beyond, these drought metrics, to really represent what we want to show? So the real question is, what timescales best reflect these different types of drought? Things like agricultural, hydrological, ecological drought. There's many, many different types of drought that are forced by different things. But in this talk, and in light of the time that we have, we're going to be focusing on agricultural and ecological drought, which are really driven by things like soil moisture. So how do we best use the tools that we have? We decided to take an approach of modeling, looking at how to best represent time series of soil moisture across the continental US to describe these kind of drought conditions. So I'm going to walk you through how we did this analysis. First, we have 260 sites, and I'll show you a map of all these sites across the continental US. And at each site, we have about 3 to 5 different depths of soil moisture time series coming from different probes. So we have about 1,000 time series for this analysis so far. So this is a typical soil moisture time series. On the x-axis, we have time. On the y, we have soil moisture. And what you can see is just a typical seasonal soil moisture time series for 3 years. The first step is we calculate drought metrics at each one of these different locations where we have soil moisture time series. And we calculate them at many, many different time scales. So from really, really short time scales, 5 to 10 day, all the way out to multi-year. So for each location, we have 150 time series of each drought metric. We then standardize our volumetric water content time series to kind of alleviate some of our statistical woes. We go ahead and correlate these different standardized soil moisture time series with all the different drought time scales, so 5, 10, 15, 20 day, all the way up to multi-year, and find the best correlation. And so this shows you the best correlation for a drought metric. This is the standardized precipitation evapotranspiration index on the secondary y-axis, and you can see we can represent this soil moisture time series pretty well using a 75-day SPEI time series. So in essence, we're going to be replicating this analysis for every single location across the continental US where we have valid time series. Here's a map of all of these locations. And I should point out that most of these sites that you're seeing are station data from NRCS data sets, such as SNOTEL or scan sites. We also have Mesonet data sets from the Montana Mesonet, which is what's filling in most of that Montana map. And we're actively looking for more and more time series of soil moisture to really increase the spatial breadth of this analysis. So please send me an email if you have any additional data sets that you would like to incorporate into this analysis. So now I'm going to show you some results and how results vary as a function of depth. So this is for the standardized precipitation index, which is a metric that really shows relatively wet or dry time periods as a function of precipitation. And on the x-axis, we have our time scale in days. So we're going from short time scales to really long time scales. And on the y, we have a density, which is basically a histogram. So this is showing you where what time scales best represent soil moisture as a function of depth. The colors on this plot represents different soil moisture probe depths. So we're going from green, which is shallow, about 0 to 4 inches. Blue is mid, about 28 to 20 inches, and deep is going all the way down to 36 to 40 inches. And that black line represents the average soil moisture time trace for each location. So what you can see is as you go in deeper into the soil column, you tend to see longer and longer time scales of these drought metrics best reflect the time series of soil moisture, which makes total sense with how you would expect precipitation to infiltrate into the soil column and that kind of overall buffering of the soil above a soil moisture probe. So in general, what you can see from this plot for the SPI is that in general, about a 60-day time scale does the best job of representing soil moisture. We did this for many, many different drought metrics, and I'm not going to talk in detail about any of them besides SPI, but what you can see from these plots on the right is that this kind of general behavior is consistent across all drought metrics. As you go deeper into the soil column, the drought metric time scale you need to reflect that time series increases. But we know that these drought metrics aren't always appropriate through time as well. So we wanted to look at how variation with season, how well these metrics work at describing soil moisture through season. So this is a plot for soil moisture on the for the SPI, excuse me. On the x-axis, we have month, and on the y-axis, we have that correlation measure. And what you can see is that when we get into the right around snowmelt across the continental U.S., right in this kind of month four, April, the correlations go way down. And this is because there's this additional input of moisture into the soil column that's not represented by precipitation alone, right? It's that stored amount of precipitation in the snow that's then being released later on. That isn't represented by this drought metric. But when we get into the later summer months and even into the fall, these times, the SPI does a really, really pretty decent job of representing those soil moisture time series, especially at that 60-day time scale. We did this again for all these different drought metrics. I'm not going to show them all here or talk about them, but really I just want to show you that this kind of trend we see that is reflected in the SPI metric is kind of reflected in most of these different drought metrics. Now, in progress, we're continuing this analysis and actively looking for more people to, to collaborate with us and to contribute soil moisture data sets. And what we want to look at is kind of variations in these spatial patterns of these soil moisture optimum timescales. So you can see, especially in Montana, there's some locations that have really long time scales. And we're going to be looking at different topographic and soil textural features of the landscape that might help explain some of the variability in these time scales. But in general, just to summarize, with the soil moisture validation, we tend to see that drought timescales increase with depth, and that's kind of across all these different drought metrics. In general, 60-day timescales are the best for soil moisture, except for when we're talking about these deep soil moisture time series at 36 to 40 inches. And drought metrics work the best in the summer and perform pretty poorly in the winter, or in the spring, really, when there's input into the soil column from non-meteorological sources or snowpack release. And then this drought dashboard that we've created is a nice way to transfer this technological assessment and empirical analysis to really try to give the best information to managers across the region. And we can update these timescales that are on the drought document to best represent things like soil moisture, but we're also going to replicate this analysis for other indicators such as things like streamflow and snowpack. And this allows us to provide tailored metrics to different regions across the upper Missouri River Basin. But as we said, this could be replicated for any region and tailored for any region across the continental U.S. And we're really, again, trying to look for collaboration to expand this analysis. So if you have any information or have more soil moisture time series you'd like to provide, please just shoot us an email and we're excited to collaborate with you. And with that, thank you. I'll pass it back to Britt.
Great. Thank you so much, Zach. So we are out of time, and I see my screen's not changing over. But thank you all for joining us today. And we will include the speaker contact information in our post-webinar email. And we appreciate everyone hanging on today. And thank you to all of our speakers for great presentations. So thank you, everyone. And we'll talk to you all again in December.